Here we go. All right. I have a couple of demonstrations that I do in the classroom for showing a magnetic field acting on a particle. And I'm going to set those up tomorrow so we can see those at the start of class before you start your test. But interesting things happen. For instance, if you have a particle that's moving in this direction, so its velocity is in that direction, and it's going through a magnetic field that might be acting in this direction, and we use the letter B in this class to show a magnetic field, and it's a vector field. And it's a charged particle. Okay, if it's not a charged particle, like if you sent a neutron through a magnetic field or a neutrino, its path would not be affected whatsoever. But if you had a, say, a proton going through here, the proton would end up having a force on it that, now I wished I'd chosen a different orientation for this thing, but the proton will experience a force in this direction. So the velocity is this direction. Wait a second, B cross B. Nope, the proton is going to experience a force into the page. So if the velocity is that way and the magnetic field is that way, the force on the proton is going to be in that direction. We could illustrate that another way if we imagine that. By the way, we're adding a third dimension here, and we haven't had to do this really in this class up until now. And a way that we illustrate this is if we draw a vector that looks like that, that means into the page. And if we draw one coming toward us, that means out of the page. It's a circle with a dot in it. So maybe an easier way to illustrate this is we'll imagine that we have a, just for the heck of it, we'll imagine that we have a uniform magnetic field here. So it's into the page. And we have a particle. So this is B into the page. And again, we use B for the magnetic field. That doesn't look much like a B, but pretend it is. Anyway, B into the page, and we have a particle that's got a velocity in this direction, and I'm just going to use a proton or an alpha particle, something like that, but the particle will end up traveling in a curve in this magnetic field, and it travels in a circle there. Okay. Now, if it's traveling in a circle, it must have a force that's inward here. And that's the way that it works with a magnetic field. In fact, we'll look at some example problems with determining the radius of curvature. But here's what the magnetic force ends up looking like. It depends on the charge of the particle. So Q, however much charge it happens to have, it depends on the velocity of the particle, and it depends on the strength of the magnetic field, but the direction of the force ends up being the cross product between B and B. And I don't know, we didn't do a whole lot with the cross product. I don't even know if we can't even remember doing torques, really. Maybe we did a tiny bit. I remember writing the symbol, but we didn't do a whole lot with it. But this is maybe our first introduction to it. For the cross product, actually, I'm going to introduce something called the right-hand rule. which we're going to use several times in different ways in magnetism, but first for the cross product, if you point the fingers of your right hand in the direction of the first vector in a cross product, so that you can curl them in the direction of the second vector, your thumb will point in the direction of the cross product. So if we have the magnetic field going into the page and we've got a velocity like this, so there's the velocity, here's the magnetic field, and assume that it's the same everywhere. V cross B is going to be to the right, and so the force on the particle is going to be in that direction if it's got a positive charge. If it's got a negative charge, the force is going to be in the opposite direction. V cross B will still be to the left, but multiplying it by a negative number reverses that. So the cross product is going to be kind of a weird thing to deal with, but try to get used to it. Do a little reading, maybe check out one of your math books. If they just talk about a little bit of a conceptual introduction to the cross product, that might help. But this is weird, and this is determined experimentally, discovering that this happens to be the way that a magnetic field exerts a force on a particle. And it's kind of strange. And the demonstrations I'll show you tomorrow will maybe help you understand that a little bit. Okay. Anyway, something about the force, though. Well, the value of a cross product, the magnitude of this force, will equal the magnitude of this, and the magnitude of a cross product, I guess I'd have to take absolute values of everything, the absolute value of Q, the absolute value of V, or the magnitude of V, the magnitude of B, and the sine of the angle between V and B. And I'm going to write that as the sine of phi. And I seem to remember doing a little bit with this fall quarter, but not a whole lot. Anyway, that's the magnitude of the cross product. If V and B happen to be perpendicular, then phi is going to be 90 degrees, and the sine of 90 degrees is 1. So that's the easiest situation to imagine in this thing. Oh, let's talk about units for the magnetic field. I need to get a piece of scratch paper. Okay, well, we've got this F equals QV cross B for the expression. We know the units of force, those are going to be newtons. Units of charge will be coulombs. Units of V will be meters per second, and then we'll have the units of B somehow. Okay, well, solve for that, and we'll get, let's see, over here on this side, we'll have newtons on top. I'm going to redistribute these units right here and have the meter by itself and the C over S there by itself, and I'm dividing by those. And so here's what I've got, and these will be the units of B. It's a Newton divided by a coulomb per second times a meter. Now, we didn't study electric current much as far as the units go, but a coulomb per second happens to be an ampere. So 1 coulomb per second is equal to 1 ampere. And usually people just call that an amp. Let's see. I think the abbreviation can be a capital A, but we're not going to deal a whole lot. In fact, it is a capital A, but we're not going to do a whole lot with that in this unit. Just keep in mind that the units of the magnetic field are going to be a Newton per amp meter. And that's different from an ampere meter, or different from an ammeter. An ammeter is the instrument you use for measuring current. An amp meter is a coulomb per second times a meter. Anyway, don't worry too much about that. But this particular combination of units is called a Tesla, named after Nikola Tesla. And he did some work in the early 20th century and late 19th century involving electricity and magnetism and electromagnetism and things like that. So anyway, that's a Tesla. Tesla turns out to be a pretty large unit of magnetic field. For instance, the magnetic field of the Earth is a few 10,000ths of a Tesla. That's a unit. There's a weaker unit for magnetism, which is a 10,000th of a Tesla. It's called a Gauss, named after another guy, but Gauss was a mathematician anyway. But that's what a Tesla happens to be. As far as talking about a coulomb per second being an ampere, I want to illustrate something. 1 coulomb per second, if I multiply that by 1 electron having a charge of 1.60 times 10 to the minus 19th coulombs, we can figure out how many electrons per second there are in a coulomb. And basically, I'm just taking the reciprocal of that thing. But the coulombs would divide out, and I'll get electrons per second. It's about 6.25 times 10 to the 18th electrons per second is what an ampere of current is comprised of. Well, what if you only have a milliamp? Well, that's 6.25 times 10 to the 15th electrons per second. So even in a little skinny wire carrying a milliamp of current, it's got a whole bunch of electrons per second moving past any point in the wire during that time. So it's a large number. But we're more interested for today in this equation and seeing some of the ramifications of it. So let's just dive in and start solving some example problems having to do with this. Okay, an electron in a TV camera tube is moving at 7.2 times 10 to the 6th meters per second. By the way, it's easy to get electrons moving that fast, but it's in a magnetic field of strength 83 millitesla. Without knowing the direction of the field, what could be the greatest and the least magnitudes of the force the electron could feel due to the field? Well, for that, the least is easy. It's 0. And here's why. So here's the force. It's going to be QV cross B. Now, the magnitude of the force is just going to be QVB times the sine of the angle between V and B. And so illustrating that, here's V, here's B, okay, and here's phi. Well, can you possibly have the sine of phi equaling 0? Yes, it equals 0 if phi is either 0 degrees. That means the velocity of the electron is in the direction of the magnetic field, or if it's 180 degrees, that's also 0, the sine of 180. So if it's anti-parallel to the field. So if you've got the path of the electron aligned just right, it won't feel any whoops, this is supposed to be the magnitude of the force, it won't feel any strength at all. So the minimum is going to equal 0 when V is parallel to, I don't know if that's a symbol it means is parallel to or not, but it should be. Or, I don't know, or anti-parallel. So, yeah, you can have 0. Maximum force is when the sine of phi is at its maximum, which happens at 90 degrees. So in that case, you just have a 1 for the sine of phi, and the force magnitude is just going to be QVB, and it is an electron here somewhere. Yes, an electron. So I'm not going to worry about the sign of the electron's charge because I just want to know the magnitude. Yeah, the magnitude of the force. 1.60 times 10 to the minus 19th coulombs times that V, 7.2 times 10 to the 6th meters per second times 83 times 10 to the minus third. And here I'm going to write this as a Newton per amp meter, even though it's a Tesla. And I've got the 10 to the minus third for the milli part of it. But then out here, I've got a coulomb per second. That's an amp. That'll divide with that. A meter. That'll divide with that. And leftover units are going to be newtons, which are the units of force we're after. So we can look at that. Eighty-three times 10 to the minus third. Okay. And I get 9 point, I guess we have just 2 significant figures because of that 83 on the thing. Got about 9.6 times 10 to the minus 14th, and newtons were the units that were left over. So, okay, it doesn't sound like much, but this is acting on an electron. And if you think of that as F equal ma, remember the mass of an electron is only 9.11 times 10 to the minus 31 kilograms. And so it's going to have a tremendously large acceleration, somewhere on the order of actually a little more than 10 to the 17th meters per second squared. So it's going to be accelerating a lot. Even with that relatively, well, just moderately strong magnetic field. There must be a part B to this. Okay, at one point, the acceleration of the electron is 4.9 times 10 to the 16th meters per second squared. What's the angle between the electron's velocity and the magnetic field? Well, the acceleration of the electron is going to be the force that's acting on it divided by the mass of the electron. We know the maximum force, but an intermediate, that's just the QVB part. Okay. And so I could write this force on top as QVB sine of phi over the mass of the electron. Well, we know what QVB is because we just calculated that. We know the mass of the electron. So let's just monkey around here a little bit. 9.6 times 10 to the minus 14th newtons times the sine of phi divided by the mass of an electron, 9.11 times 10 to the minus 31 kilograms Remember that a Newton per kilogram is a meter per second squared. So in this situation, we have an acceleration that's less than that. It's 4.9 times 10 to the 16th. A equals 4.9 times 10 to the 16th meters per second squared, which is going to equal, now I'll actually calculate this thing. This is okay, 1.05 times 10 to the 17th meters per second squared, and I still have that sine of phi there. So the sine of phi will equal this divided by that number, 4.9 times 10 to the 16th meters per second squared divided by 1.05 times 10 to the 17th meters per second squared. These are just astounding accelerations, but they kind of let you realize we're not going to have to worry about gravity when we're studying this stuff most of the time, because these accelerations are so many times greater than the acceleration due to gravity that it's just not going to show up. Anyway, let's see. Okay, I get 0.18 for that sine of phi. So the angle phi is going to equal the inverse tangent of that. And I don't know what it's going to be. Some number of degrees, because my calculator's in degrees mode. I get 10.10 degrees. Yeah. Degrees. And that's actually 10.4 is what I get. So to two significant figures, it's 10 degrees. Just indicate that. So there's our first problem having to do with this. And getting to use this equation, the cross product, a little bit, investigating some properties of it. Let's try another. Magnetic fields are often used to bend a beam of electrons in physics experiments. What uniform magnetic field applied perpendicular to a beam of electrons moving at 1.3 times 10 to the 6 meters per second is required to make the electrons travel in a circular arc of 0.35 meters? Well, that's kind of interesting. So this dot ought to work. Okay, so here's our little an overhead view of this, and this would be the center of it. The radius of this is 0.35 meters. And let's just investigate this a little bit, maybe for future reference as well. But if we have the magnitude of the force is QVB, and this is, let's see, I left off the sine theta or sine phi because we're going to assume that the velocity and the magnetic field are perpendicular. So the plane that this electron is traveling in, yes, electrons, not just one, is perpendicular to the magnetic field. So the magnetic field is either pointing down or up. And in fact, if the electrons are traveling in this direction, V cross B would point to the inner thing, but QV cross B would point that direction because the electron has a negative charge. So the magnetic field here must be pointing up out of the page for from this viewpoint to get a counterclockwise circle. But that'll equal that, but that'll equal MA, which in this case is MV squared over R when it's traveling in a circle like that. And so let's see, I can say that QVB equals MV squared over R. And let's see, I can divide out one of those things. We want to know the strength of the magnetic field. So we can just solve for that. But sometimes we may just want to solve for R. And if we do that, let's see, I'd have MV squared divided by QVB, which actually reduces to MV over QB. So that would be the radius of circle when you've got the velocity perpendicular to the magnetic field. But in this case, we're after B. So let's solve for that. I can divide a V out of both sides, and I'll have MB over Q, I think. Is that going to work? Let's see. I think it will. Let's plug in the numbers and see what happens. Electrons again, 9.1, whoops, 11 times 10 to the minus 31 kilograms. The speed was 1.3 times 10 to the 6th meters per second. Yeah, this ought to be fun figuring out the units on, I guess. Let's see, 1.660 times 10 to the minus 19th coulombs. I'm wondering, let's see, I can see, oh, I know what I need to do. I need to multiply top and bottom by 1 over a second. Why do I do that? Well, on top, I'll have a kilogram meter per second squared that way, which is a Newton. And on the bottom, I'll have a coulomb per second, which is an amp. But I need a Newton per amp meter. Let's see. Did I mess up something here? Okay. MV over QR. Oh, I was supposed to have QR down here. That's what's wrong. Yeah, and so I still have R, the radius. Okay, that's what I lost. Anybody make a note of that? Nope, missed it. Okay, anyway, the radius in this case was 0.35 meters. Okay, and then I've got a Newton on top and a coulomb per second, which is an amp, and I've also got a meter there. So I'm okay. That's an example of looking at the units. I found a mistake I'd made. I'd lost the R, so we can do that. But anyway, the magnetic field in this case. And I get not a real strong one, 2.11 times 10 to the minus 5th Tesla. So let's see if that makes sense. That'd be minus 25 about. Actually, minus 24. That'd be minus 5th. Yep, that works out about. So not a super strong magnetic field, but you could make something like that. Although in this case, that's actually weaker than the Earth's magnetic field at most places. So if you were trying to study these things, you'd have to take into account the strength and direction of the Earth's magnetic field and somehow try to set the experiment up so the Earth's magnetic field didn't disturb your particles traveling in a circle, which is going to be kind of weird because they are traveling in a circle. So might not be such a good experiment to try. Maybe speed them up and have a stronger magnetic field. That could do it. Okay. Here's one related to astronomy. Show that the radius of curvature of a proton moving at a velocity of 25 kilometers per second in a magnetic field of 10 to the minus 10th Tesla is small compared to interplanetary distances. Now that's a pretty weak magnetic field, but it might be an example of a magnetic field strength out in space. So Earth's magnetic field on the surface might be around a 10,000th of a Tesla, 10 to the minus 4th Tesla. But when you get farther away from the Earth, the strength drops off like the square of the distance. So that could be what it is. The protons therefore spiral around interplanetary magnetic field lines, and we say that they're tied to the magnetic field lines in cosmic magnetic fields. Okay, well, first, what's an interplanetary distance like? When we had our unit on gravity, we dealt with astronomical units, but we didn't really mess around with that. But one astronomical unit, which is the semi-major axis of Earth's orbit, is about 1.50 times 10 to the, let's see, it's 150, 1.50 times 10 to the 8th kilometers. Actually, it's 10 to the 11th meters. So that's what an astronomical unit happens to be. And so figure interplanetary distances might be a third or a fourth or a fifth of something like that, maybe the distance from Earth to Venus at closest approach. So we'll see how our answers compare to that. Okay, so we just did a thing where we figured out the radius of curvature, but let's go through it again. F equals QVB equals MA, which for a circular path is MV squared over R. Or if we solve for R, we'll get R is equal to MV squared over QVB, which is MV over QB. All right, so this will just tell us the radius of curvature of these things traveling around. And again, oh, this is a proton, so it's got more mass, 1.67 times 10 to the minus 27th kilograms. The speed, 25 kilometers per second is, oh, let's see, 25 times 10 to the third meters per second, or 2.5 times 10 to the fourth meters per second. And then divide by the charge on that thing, 1.60 times 10 to the minus 19th coulombs. And then the magnetic field strength, I'll just say 1 times 10 to the minus 10th. And it's a Tesla, but I'm going to write it as a Newton per amp meter so I can keep track of what I'm supposed to do with these things. Yeah. Okay. I'm going to check this out on the bottom. I'll have coulombs times coulombs per second times meters. And a Newton is a kilogram meter per second squared. Meters go away, coulombs go away. That second will flip up top, and I'll have kilograms per second on the bottom. And on the top, I've got a kilogram per second as well, and I have a meter. So I'm going to end up with meters for units. That's good. Okay, and I get 2.6 times 10 to the 6th meters, except we've only got 1 sig fig pretty much. So 3 times 10 to the 6th meters. But that's way smaller than 1.5 times 10 to the 11th meters. And so pretty small. In fact, this is smaller than the radius of the Earth. So yeah, tied to magnetic field lines. By the way, when you have a charged particle that has a velocity that part of which is parallel to the magnetic field and part of which is perpendicular to it, in the expression QV, whoops, this is the one with the arrow, QV cross B, you can split that velocity into two parts, and you'll have Q, a parallel part, and a perpendicular part. Whoops, and this is cross B. And so you get this expression where it's QV parallel crossed with B plus QV perpendicular crossed with B. And remember that cross product has magnitude of this, magnitude of that, sine of the angle between them. Well, the angle between V parallel and B is either 0 or 180 degrees, depending on if it's parallel or anti-parallel, but this thing is 0. And so the magnetic field has no effect on this parallel velocity, but it does have an effect on this, making the thing travel in a circle. But what you get is a helix. So the particle keeps circling along like that, but continuing to travel in this direction. And I may not have done that good a drawing, but that's what happens. And these particles travel along magnetic field lines like that. And then if we imagine that there's this thing sitting here that's got, this is the North Pole up here, and this is the South Pole down here. Well, it turns out the Earth's magnetic field is as if we had a giant bar magnet inside the Earth, and the North Pole of that bar magnet is actually close to the South magnetic pole, and the South Pole of the bar magnet is close to the North magnetic pole. But the magnetic field of this particular configuration is something that is shaped like this. It's like a dipole electric field. And the reason that your compass magnet points north is because opposites attract, and it's pointing to a south magnetic pole, which is actually near the magnetic north, or the geographic North Pole of the Earth. But here's what happens. The sun puts out a continual stream of charged particles, sometimes more, sometimes less, sometimes a lot more. It's called the solar wind, and it's just the sun blowing off these charged particles. For the most part, it consists of protons and electrons, but there are other things in there as well. Mostly though, just protons and electrons. And occasionally it'll put out a big blast. But what happens is these particles coming from the sun get trapped by the Earth's magnetic field lines and they will spiral around them and then come down and smack into the Earth's atmosphere down here. And they may not be in that tight of a loop, but when those charged particles, and if they were charged oppositely or if they were approaching this part, they can spiral down and hit down here in the southern hemisphere. But when those things smack into atoms in the Earth's atmosphere, they give off light. And that's what causes the aurora borealis, which you can see in the north, and the aurora australis, which you can see in the south. And a year ago, actually about a year and a month ago, I had the pleasure of traveling to Iceland during the middle of March and was able to watch some absolutely spectacular aurora there and tried to take pictures of it, but mostly I just sat back and leaned against the hood of the car and enjoyed the show. They were just amazing and really fun. If you ever get a chance, go there. But don't go in the summer because it never gets dark and you can't see aurora when it's light out. Okay. Let's move along on these things. In a certain region, the average radius of curvature of the trajectory of electrons trapped in the Van Allen belt, that's a belt around the Earth. And electrons, the Earth's magnetic field can trap electrons in there. Anyway, the average, let's see, 300 meters for the radius of curvature. Average electron energy is 100 keV. Now, this will point something out. I noticed on homework 2, there was a problem with people thinking that an electron volt was a volt, and it's not. It's a unit of energy. So the K there means we'd multiply by 100 or 1,000. And so this would be 100,000 electron volts. So the energy is 100,000 EV, which is 1 point, I don't know how many significant figures, none or 1. So 1 times 10 to the 5th electron volts, but we need to multiply that by, there is 1 joule for every, no, that's not right. There's 1.60 times 10 to the minus 19th joules per electron volts. And so that gets rid of the electron volts and gives us joules, which is something we can actually work with. And this will give me kind of a phony 2 significant figures. Yeah, let's just figure out the Earth's magnetic field to 1 sig fig and round that to 2. So I'd have 2 times the energy of these electrons, 2 times 10 to the 14th, 10 to the 5th, and 10 to the minus 19th joules. And that'll be 1/2 mv squared. So let's see. Didn't we do something where we figured out a radius of curvature? So, or F equals QVB equals MA, but that's MV squared over R. Oh, how convenient. I've got an MV squared there. So I just need to multiply top and bottom by 1/2. Excuse me. And we're after B. So, oh, rats. I'd have B divide out here. Maybe I should, yeah, is there any way? Oh, well, we can figure it out. V is going to equal, let's see, multiply I'd have 2 times 10 to the 14th joules divided by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And I have to take the square root of that to get V. So no way around it. Had to do that work after all. Whoops, into the 1/2. That's so I can evaluate this expression. Anyway, 2 times 10 to the 14th divided by oh. Yeah, that was from rounding that. I've got a 1/2, so I'd actually have 4 times 10 to the 14th here. Hmm. You know, I bet that's supposed to be a minus 14th. That would make a lot more sense, wouldn't it? Okay, let me try this calculation again. Yeah, I was getting a speed of about 10 to the 22nd meters per second, which is almost 3 times the speed of light, which is kind of impossible. Anyway, now 4 times 10 to the 14th is what I need here, because I had multiplied out from underneath by 2. Minus 14th. Do it right this time. I still get a pretty good clip on this thing. Um, 2 times 10 to the 8th meters per second. That's a relativistic velocity. That's 2/3 of the speed of light. So technically, we should be using relativity to evaluate this, but to one significant figure will be okay. So now the magnetic field strength, if I divide by Q and that, it's going to be MV over QR, where that's the radius of curvature of this thing. And it's only a V because there was a V here and I divided it out. So 9.11 times 10 to the minus 31 kilograms times 2 times 10 to the 8th meters per second divided by Q, it's an electron, 1.6 times 10 to the minus 19th coulombs. And the radius of curvature was 300 meters. Okay, now I need to turn this into a Newton on top, so I multiply top and bottom by 1/seconds, which is multiplying everything by 1, and then I'll have coulombs per second times a meter on the bottom, or an amp meter, and a Newton on top, and so I'll have Teslas for the strength of the Earth's magnetic field. So let's try it out. I have to do tricks like this a lot, especially in this magnetism unit, to get things to make sense with the units, because I definitely don't trust like on that last problem where I dropped the radius. I don't trust myself just saying, oh, it's got to end up being Tesla. I need to check it. And I get not real strong, 4 times 10 to the -6 Tesla. So this would be the Earth's magnetic field, but it's out a ways away from the surface of the Earth, so it gets weaker out there. Anyway, another kind of astronomical problem. The Van Allen belts were predicted by a scientist named Van Allen before we had ever put anything into space. And on some of the earliest satellite missions, they were testing for the existence of those things, and the hypothesis was confirmed. Well, I think we can get through 5 of these 6 problems today anyway. This may be the last one. S.A. Gouchschmidt devised a method for measuring accurately the masses of heavy ions by timing their period of revolution in a known magnetic field. A singly charged ion of iodine makes 7.00 revolutions in a field of 45.0 millitesla in 1.29 milliseconds. Calculate its mass in atomic mass units. This is actually, it's different from a mass spectrometer, but I just listened to a talk last week named after a guy at the University of Minnesota who pioneered and measured the masses of a lot of ions, or not ions, but well, they were ions, but they were also isotopes of some of the heavier elements. And he did it using things traveling in magnetic fields. In fact, one of the applications we'll look at is a mass spectrometer. But how could we get this? Let's look at what we've got so far. We know that F equals QVB equals MV squared over R. We haven't talked about time yet, really, but the time that it would take for a revolution would equal 2 pi r. Well, actually, the speed that they're traveling around a circle in is going to be 2 pi r divided by the time they take for a revolution. So the time for a revolution is going to equal 2 pi r over v. So can we do something to get an r over v here? Well, we've got a v over r, right? If I go QB is equal to m times v over r, and that would do it. Let's see. And I'm after the mass. So if I divide this or multiply both sides by r over v, I'd have r over v times q times b is going to equal the mass of this thing. And if I multiply top and bottom by 2 pi over 2 pi, I can take this much of it, and that would be the time for one revolution. So T times Q times B divided by 2 pi will equal the mass that we're talking about here. So this made 7 revolutions in 1.29 milliseconds. So I can figure out what the time for a revolution is. It's 1.29 times 10 to the minus third seconds divided by 7.00. Oops, turn on the calculator first. Okay, so the period for a revolution is 1.84 times 10 to the minus fourth seconds. So I can plug in here and see what we get. 1.84 times 10 to the minus fourth seconds times, let's see, charge, was it singly ionized? Singly charged ion. Yep. So 1.60 times 10 to the minus 19th coulombs. Chances are this is a positive ion because the way they test them in here is to have their velocity go in one direction and have a beam of electrons going perpendicular to that will knock an electron off of the particles and turn them into a singly charged positive ion. And we have a magnetic field of 45.0 times 10 to the minus third Tesla, but I'm going to call it a Newton per amp meter again so I can check to make sure my units came out right. And then on the bottom, I just have a 2 pi. Okay, well, let's see. That Newton per amp meter simplifies to, let's see, that's a kilogram meter per second squared is a Newton. And down here, I've got a coulomb per second times a meter. So the meters go away. I've got, oh, what am I multiplying it by? So there's my Newton per amp meter. It turns out into a kilogram coulomb per second is actually what it turns into. Kilogram coulomb per second. No, it doesn't. It's a kilogram per coulomb second because you invert this and multiply. So, and the coulomb goes away, the seconds go away, and I'll end up with kilograms. Good. Okay, so the mass of this thing is going to be 1.84 times 10 to the minus 4 times 1.6. It's going to be a small mass because it's a molecule, or it's just an ion of iodine times 45 e minus 3 divided by 2 pi. And I get 2.11 times 10 to the minus 25th kilograms, but need to get it in atomic mass units. So I multiply that by 1 AMU. And the mass of a proton mass is it's 1.67 times 10 to the minus 27th kilograms. But an atomic mass unit is a little less than that. It's 1.66 times 10 to the minus 27th kilograms. So 1.66 times 10 to the minus 27th kilograms. So this will be some number of atomic mass units. Should be close to an integer. And I get 127. Now, it said it's an iodine. Oh man, is there a periodic table handy? Probably in the appendix of the textbook, I hope. Somewhere. I can't remember. Oh, here we go. Iodine, atomic number 53. So this is an isotope of iodine that has 53 protons, 127 nucleons. Because when you get this number, that's the number of nucleons it has. So whatever 127 minus 53 happens to be, looks like 74. So this isotope of iodine has 74 neutrons. It only asked for this, but that identifies what isotope it happens to be. Okay, I'm going to stop there. I hope to see all three of you and everybody else this evening at 7:30 for a review session for the test. And I think what I'd like to do for that, actually, I'll stop the recording here.